Hey gents, back again to talk about this time about the simple pendulum. Um, I'm sure the cat's out of the bag on this one too, since we're into homework. That would include this. So we see here on the screen we have the period of a simple pendulum. It's an equal sign, which we should take with a grain of salt, as we'll kind of see as we go through. But it's equal to, quote unquote, 2 pi square root L over G. There are some assumptions that go along that make this equal sign better. And that is if we keep our angles less than 15 degrees, the real period and the period calculated by this equation here will be 1% error at 15 degrees roughly. And as the angle gets smaller, it's less. We also, since it's called a simple pendulum, there's some idealization going on. One, the string itself of the pendulum would be massless, and really it can't bend either. And also the mass is a point mass. I don't know what happened to my two S's there, but that should say mass. I'll need to get that fixed up. Also, the length of the pendulum, if we're going to have a real mass behave like a point mass, as long as the length of the pendulum is much bigger than diameter. So like a 10-to-1 ratio. This is a colon, excuse me. 10-to-1 ratio gives pretty low error. So let's go to our data that we looked at. I took all the data you guys generated. I took it over to Excel because I think it graphs better. And let's take a look at period versus little g. Like you looked at and you probably noticed that there is an inverse square root relationship between period and little g. We can see the negative square root right there. So this is on the bottom. And we can see a relationship here that should be giving us some strong hints about stuff. All right, go to the t versus the length, and you'll notice that we have a relationship between L and T that's a square root of L is proportional to T. Again, a very good match. We have some outliers here that probably were just the wrong mass or the wrong little g or something. T versus M, as you probably noticed, there's not really much relationship between T and M. And then the weird one, T versus theta. And so I threw all of these fits up there on the graph for you guys to look at, just to show none of them really work well for the data that goes all the way out to 180 degrees. So this shows that the exponential fit's not so hot. This shows that a linear fit's not so hot. This shows that polynomial's not so hot. This shows that the power fit is atrocious. So we don't really have a good fit. And so what I did is I went back to our data and I pulled out just all the angles that are less than 30 degrees, and I plotted t versus that. And you'll notice that if we have the period here versus angles less than 30 degrees, which is just a smaller chunk, basically this chunk over of this bigger graph, the t versus theta graph, and we can see that it's not too huge of a difference. This is 2.04. This is about 2.005, so it's not a huge difference. But what I did is I took all the things that we kept constant, little g, 9.8 meters per second, and L of 1 meter, and I used that equation here. Use this equation, put in 1 meter, put in 9.8 meters per second, and I calculated, and I got 2.007 seconds. And you'll notice that if we're down here close to 15 degrees or less, we're very close, especially 10 degrees or less are pretty darn close. So what I did is I went back and I calculated, hey, what's the percent difference between, say, this data point and the 2.007? By what percent are they different? And I plotted that. And you can see, and I used the absolute value, so I didn't have any negative values down here. If you look on this graph, I would get some negative percent difference values. I just did the absolute value, so everything remained positive. And you'll notice that this line right here is a percent difference of 1%. Notice that if we stay below 15 degrees, we're darn close to less than a 1% error between what the period was and what our equation would calculate. And what I mean by our equation is what this equation would calculate, which gave us, come on, respond. which gave us this orange line here. So our equation gave us that, and we're really darn close here. So as long as we keep those angles less than 15 degrees, we're right around 1%. That's about 1.1% error. So what I did is I took suggestions, which the suggestions essentially matched, hey, Mr. Sorensen, we think this equation right here should give us the period of our simple pendulum. So I used our constant G data, the same data that we plotted here. I'm sorry, the same data that we plotted here. This is constant G data. This is little g is 9.8 meters per second per second. So with little g at Earth gravity, I let L change. So this is L down here, and you'll notice here's the period. And I have essentially a number here that's very close to 2 pi times the square root of L over G with a y-intercept that's practically 0. And this tells me that that equation here is a really good fit. I have some outliers that I didn't bother to fix, but it looks pretty good. Then I took the data where L is constant, which is this data here. We let little g vary. And so L is constant at 1 meter. Plug that in, and I got, again, using the equation that was suggested of square root L over G would give us a linearized graph. And you'll notice that this out front is very darn close to 2 pi. And this right here is the intercept is very darn close to 0. And the fit is really good in that linearized graph. So part of the reason that this theta thing is so strange, let me zoom in on this one. The reason why this the different angles is so strange is the restoring force. There is not really a restoring force, it's a restoring torque. So little g is acting over different perpendicular distances to the pivot point, which is the top of the pendulum, and that varies with angle. So the restoring torque is going to vary as the angle changes. And so as long as we keep the angle small, our approximation, this approximately equal to 0 works really well. And we'll see in the video here coming up some other things that does for us. But this is all we got. So looks good. Thanks, guys.